Okay, we want to look at the, again, work energy implications of moving from an orbit at distance r1 to an orbit at distance r2, where r2 is greater than r1. In order to do this, our total energy, our potential plus kinetic energy, is going to be negative 1/2 big G, big M, little m, times 1 over r2 minus 1 over r1. This follows directly from what we did in the last clip. Now this looks like it could be a negative number, so I'm going to rearrange it here. I'm going to change the signs of the 1 over r2 and the 1 over r1 to get rid of the negative side. I can just think of distributing the negative sign through here and then putting them in the order with the minus in the middle here, okay? So that looks a little more like it ought to be positive. Of course, if r2 is less than r1, it isn't. So it's just a matter of taste how we rearrange that. But we have to understand that if r2 is greater than r1, the change in total energy is positive. So that the potential plus kinetic energy is not constant. It increases by this amount. And that implies, by the work energy theorem, that the work done by non-conservative forces on the system, which is equal to delta PE plus delta KE, is 1/2 big G, big M, little m, times 1 over R1 minus 1 over R2. Okay, now where does this come from? We got to get this work. From somewhere. Otherwise, the satellite ain't going to go from here to there. Okay? Well, it goes from here to there by virtue of non-conservative force exerted by what? What do you think? Well, in the case of a satellite, at least with the technology we have right now, and any technology we can foresee in the future, it does this by rocket engines. Now, I'd say it does by rocket engines. You can do it with a solar sail. Might take you years, but you could do it with a solar sail also. So that wouldn't be a rocket engine. So we could mention a solar sail. Etc. It'd be interesting second semester when we talk about how solar sails work and what the energy source is there, and basically how photons interact when they collide with a solar sail. Okay, the fact that photons have momentum, etc., etc. Okay, that's a little digression, but that's the situation. That's the overview of the situation. Now, if we're trying to get a satellite from here to a speeding comet, we've got to build up a lot of speed relative to the Earth. How do we do that? How do we spiral out to that comet? Why does it take 10 years? It's not all that far away. And that's an interesting discussion. We're going to lay the foundations for understanding that. But we're probably not going to get into the detailed mechanics. One thing I do want to do, though, to get into the detailed mechanics, is think about how we would go from one circular orbit to another. So my next question is going to be how to get from the first orbit to the second. What do? We don't just drive from here to there. We don't just fire the rockets and point out there where we want to go because the Earth's gravitational field is going to cause us to deflect our path in the direction of the field. We don't just go straight away from the Earth from here to there. We would have to supply enough potential energy to get from here to there, and that's twice as much energy as we need. So what are the implications? What are the mechanics? We'll do that in another clip.